and also discuss digital systems today. In the previous lecture yesterday, we had discussed why digital signal processing, and even if the signal is analog, why one processes by digital means and what the processing involves: sampling hold, A to D, DSP, then D to A, finally followed by an analog low pass filter. We had enumerated the advantages of DSP. The major advantage, the dominant advantage, is linear phase. For communication engineers, it is a boon that there is no delay distortion in processing a signal. We also said that a digital signal processor, the same processor, can be used for handling more than one signal by a process known as time multiplexing. DSP is less sensitive to element tolerances and environmental changes. The accuracy and range of DSP, dynamic range, can be increased almost without limit if you are prepared to spend money. The cost also increases. Storage of digital signals is no problem. It can be done on magnetic tapes, discs and other media. Low frequency processing is no problem because there is no inductance to bother about, and the characteristics of a DSP can be changed very conveniently by changing one or more coefficient. It is simply changing a number. But then we also said that DSP is not all advantages, it has its own demerits. First is that the hardware complexity is much more than in analog signal processing. Then there is a limitation on the highest frequency that can be used because the sampling frequency is limited. For sample hold and A to D conversion, it is limited. Current status is about 10 megahertz. You cannot go beyond that. So the signals that you can handle can go only up to 5 megahertz, half of the sampling frequency. Then power dissipation is a problem, but I have told you that research is on to reduce the power as much as possible and ultimately to zero, because particularly for implantable devices where the aim is that the device should work from body temperature. We introduced sequences, right sided, left sided, general sequences, even sequence, odd sequence, and we said that any sequence can be broken up into its even part and odd part. Then we talked about bounded sequences, absolutely summable sequence, finite energy sequence or square summable sequences, and then we also defined a quantity called average power. For a periodic signal, average power needs to be calculated over one period only, because every period is a repetition of another period. Then we introduced the elementary digital signals, namely delta n, the unit impulse, and u of n. Delta n is the most elementary signal and it differs from delta t of analog signals in that it is much simpler. Its amplitude is simply 1, it occurs at n equal to 0, and u of n can be represented as a combination of delta n minus k equals to 0 to infinity, and delta n similarly can be represented as u of n minus u of n minus 1. Okay. So, this is the relationship between delta n and u of n, and any arbitrary sequence can be expressed in terms of u of n and delta n. Let us take an example. Suppose you have a sequence which starts from 0, then 1 at 1, 2 at 2, and let us say 3 at 3, 1, 2, 3. Okay. Obviously, we can write this as, suppose this signal is x of n, all other samples are 0. This goes without saying. Whenever we draw a finite length signal, what is the length of this signal? 4. Okay. Because the sample at 0 also has to be taken into account. You might say its length 3. This 0 could belong to these zeros, all right. So, there is a fuzziness here, okay. But we can obviously write this as delta n minus 1 for this signal plus twice delta n minus 2. We can also plus 3 delta n minus 3. So, we have expressed x of n in terms of deltas. X of n can also be expressed in terms of u of n as u of n minus u of n minus 4. What is this? This is a gate from 0 to not 4, 3, because u of n minus 4 is subtracted, and therefore, this represents this gate, and we see that the amplitude is proportional to n. So, we simply multiply by n. Agreed? Any arbitrary signal, there are a large number of problems in the textbook, you should work it out. Any arbitrary signal can be expressed in terms of u of n and delta n. Now, one sequence that is very often used is the so called exponential sequence. Exponential sequence, and exponential sequence is of the form some constant a alpha raised to the power n. In other words, the sequence is, if it starts from n equal to 0, then a alpha squared, a alpha cubed, and so on. If it starts at n equal to infinity, then it starts from a alpha to the power minus infinity, then it reduces a alpha to the power minus 1, a, then a alpha squared, and so on. Now, if this extends from n equal to 0 to infinity, the way to ensure this is to multiply this by u of n. U of n is 0 for n less than 0, and it is 1 for n greater than equal to 0, and therefore, this ensures that this is a right sided signal starting from n equal to 0. Is this a bounded sequence? Is this a bounded sequence? Obviously not. If alpha magnitude is less than 1, then it shall be bounded sequence. Agreed? If alpha amplitude is less than 1, then it is a bounded sequence, whereas if magnitude of alpha can be complex, alpha can be real, alpha can be positive, alpha can be negative, but if magnitude of alpha is greater than 1, then this right sided signal is not bounded, because it increases indefinitely to infinity. If it is not right sided, if we take the general signal a alpha to the power n, then is this bounded? Are there some conditions which will make it bounded sequence? know whether alpha magnitude is greater than 1 or less than 1. If alpha magnitude is less than 1, then the right side is bounded, but the left side will become unbounded. Suppose alpha is 0.5, then 0.5 to the power minus 1 is 2, 0.5 to the minus 2 is 4. So, it goes on increasing on the left hand side. So, this signal in general is unbounded irrespective of the magnitude of alpha. And then we consider the most important signal in practice, and information is transmitted only by such signals, a combination of them, that is the sinusoidal signal. Sinusoidal signal, and the most general signal, cosine or sine does not matter, a cosine omega 0 n plus some phase, let us say phi. This is a sinusoidal signal. Is a sinusoidal signal a bounded signal? No, bounded refers to the amplitude, not the extent. It is a bounded signal because the maximum value is capital A. So, it is a bounded signal. Is it a periodic signal? Periodic, the answer is not an unconditional yes. It may be periodic, it may be non-periodic. If it is to be periodic, then if we denote this by x of n, then there must exist a quantity capital N such that it is equal to x of n. Agreed? Let us test whether it is periodic or not. We have cosine of, forget about A does not affect the periodicity or otherwise. Suppose you have cosine of omega 0 n plus n plus phi. If this is to be equal to cosine of omega 0 n plus phi, then obviously omega 0 capital N must be equal to an integral multiple of twice pi. So, it must be twice pi r, where r is an integer. Okay? In other words, omega 0 by 2 pi must be equal to r by n. Now, this is not guaranteed. Omega 0 by 2 pi, that it would be a rational number, that is an integer divided by an integer, is not guaranteed. For example, cosine of 3n is not a periodic function, because 3 divided by 2 pi, pi is not a rational number. Pi is not 22 by 7, it is infinite number of digits. Okay? So, cosine of 3n is not a periodic signal. In other words, while all analog sinusoidal signals are periodic, a digital sinusoidal signal may or may not be periodic. Is that point clear? Suppose we have 3 signals, let us say x1 of n, x2 of n and x3 of n, and suppose each of them is periodic, of period n1, n2 and n3, and then let us make a combination of these 3 signals, that is, I multiply x1 by alpha, x2 by beta and x3 by gamma. Let us call this as x4 of n. I make a linear combination of these 3 signals. The question I ask is it periodic? It is surely periodic. But the period is the period n4, period of x4 is the lowest common multiple LCM of n1, n2 and n3. Let us take an example. Suppose N1 is 3, N2 is 5 and N3 let us say is 12, alright. Then the LCM of 3, 5 and 12 you can easily verify is 60, isn't it right? Because 12 is 3 multiplied by 4 and 3 is already contained there. So, it is 60. After 60 cycles X1 executes 20 periods, isn't that right? 20 cycles. After 60 cycles N2, that is X2, executes 12 complete cycles and X3 executes 5 complete cycles. So, at this number 60, each of them must have completed an integral number of cycles, and therefore, the combination is periodic with a period of 60, alright. So, sum of digital periodic signals is also periodic. If these are prime numbers, for example, one is 3 and the other is 15, it is simply 3 times 5, 15. But if they are not primes with respect to each other, then you have to take the LCM of these 3 numbers to get the total period. Now, we go a little more into the interpretation of this signal A cosine omega 0 n plus phi. How does one obtain such a signal? Suppose you have an analog signal A cosine omega 0 t plus phi. Okay. Let us take in general omega n plus omega t plus phi. Okay. Then to obtain this signal, this is a digital signal, how do you obtain it? Sample it at every capital T, then what you get here is A cosine omega n capital T plus phi, and after A to D conversion you get A cosine omega n plus phi. So, what is omega? Omega is capital omega multiplied by T, which I can write as omega by Fs. Fs is the sampling frequency, that is equal to 2 pi the actual frequency in hertz. Capital omega is in radians per second, F is in cycles per second, hertz, divided by Fs. And therefore, you can also write this as 2 pi omega divided by omega s, ratio of angular frequencies or ratio of hertz frequencies, cyclic frequencies. You notice that small omega, capital omega was in radians per second, but small omega has lost its unit because F by Fs, it is dimensionless. Omega by omega s is dimensionless. So, how should you express omega? Omega is a dimensionless number, but we express this in radian. Why? Omega is an angle after all. Does radian have a dimension? No. An angle is arc divided by radius and therefore, this small omega, the digital frequency, is in radian, not radians per second, all right. It is called, omega is called, it is given a name, normalized digital frequency. Normalized digital frequency. Now, let us recall what omega is. Omega is 2 pi f, the actual frequency, divided by Fs, and we shall soon see that in digital signal processing we cannot go beyond half the sampling frequency. then there is distortion, and therefore we have to be limited. So omega max is equal to 2 pi Fs by 2 divided by Fs, which is equal to pi, right, and therefore the range of normalized digit frequency is 0 to pi, and for a real signal, whatever positive frequency is there, there must exist a negative frequency also, and therefore the actual range of omega is minus pi to plus pi, and this is called the base band, or the band of vision, the band where you have to focus your attention. In DSP, this is an advantage, this is fortunate that our range of vision, we do not have to go to infinity, our range of vision is limited between 0 and pi, if you want to plot the magnitude and so on. It is only positive frequencies that we bother about, but you must keep in mind that our range of vision in the spectrum domain is minus pi to plus pi, whereas in analog frequency you have to go from minus infinity to plus infinity. The whole range is now compressed to minus pi to capital Pi. This makes life simple. You do not have to compute beyond pi, but you must remember that small omega is a normalized frequency. It is not the frequency in radians per second, it is in radians. We shall come back to why the restriction on f a little later. Now, digital signals can be subjected to some operations on sequences. First is multiplication. If a sequence x of n is multiplied by another sequence y of n to form a new sequence, let us say w of n, it means that the corresponding samples are multiplied. That is, n equal to 0 sample in x of n is multiplied by y of 0. W of I, the ith signal in w is obtained by ith signal of x multiplied by ith signal of y, and the symbol used for it, multiplication, which is nothing but repeated addition, is y of n, x of n, and then w of n. See, multiplication is a non-linear operation, and very few instances we resort to multiplication, to a non-linear operation like this. However, as you shall see later, in FIR filtering we do use multiplication of two sequences. We multiply the given sequence by what is called a window function, and there does exist cases where the multiplication has to be resorted to. One more point before you go to the next operation. Suppose the two sequences are not of the same length. Suppose x of n is of length 3 and y of n is of length 7. Then how do you multiply? Because the fourth sample in x of n is not there. Okay? Fifth is not there. So you pad zeros. That is, before doing any operation, you make the two lengths identical by adding zeros to the sequence which has less number of samples. Okay? This must be remembered. Then addition or subtraction. A similar procedure, that is, when you add Wn, when you add x of n to y of n, add or subtract, then the corresponding samples are added to form the new sequence Wn, and the symbol that we shall use is the summation sign, two inputs x of n and y of n, and if it is simply addition, then we do not assign any sign to the arrows, but if it is subtraction, then we assign a negative sign here. So, in general it would be plus minus, but plus sign we usually avoid. Negative sign simply means that this sequence is to be multiplied by minus 1. Minus 1 is not a multiplier, it is simply changing the sign bit of the binary number. Okay. So, we do indicate a minus sign only when subtraction is involved. If addition is involved, we do not do that. One more point that needs your attention is, in digital signal processing, as you know, in digital hardware, we cannot add more than two numbers at a time. In accumulator, we feed numbers in sequence and it accumulates, it adds the number, replaces the storage by the result, then takes another number and so on. So, this discipline we must exercise. In other words, whenever we have to add three numbers, for example, or three signals, we shall use two summers to indicate the steps that are involved. All right. And then multiplication can be of two signals or can be by a scalar. For example, if you have x of n and you wish to multiply this by alpha, then what you do, the symbol that we shall use is, we shall simply use alpha inside the circle and the output is alpha x of n. This is a scalar multiplication. It is not multiplication of two sequences. If the multiplication of two sequences are involved, we use a cross, whereas this is a scalar multiplication. And then we have time reversal, that is, given an x of n, the time index is reversed, that is, you find an x of minus n, well, which simply means that you flip over. If this is a right sided signal, then you flip over and make it a left sided one. If this is a left sided signal, flip over and make it a right sided signal. For example, as you know, u of n is 1 for n greater than equal to 0, u of n. What is u of minus n? It starts at n equal to 0, because minus 0 is the same as 0, n equal to 0, and then goes to the left. Okay. Suppose suppose I have a signal, I am tempted to do this. Suppose I have a signal which does not start at 0, but it starts at minus 1, minus 2, and it is 1 on the left hand side. What would you call this signal? What would you call? Can it not be u of minus n minus 1, u of minus n minus 1. The definition of u of n is it starts at n equal to 0, the argument equal to 0. Where does this start? Minus n minus 1 equal to 0, so n equal to minus 1. So, this signal is u of minus n minus 1. Suppose I take u of n plus, is this point clear? U of minus n minus 1, u of minus n minus 2 will start at n equal to minus 2. Okay. Suppose I take this sum, u of n plus u of minus n. What is this signal? It is 1 everywhere except at n equal to 0, where the amplitude would be 2, and therefore this is, can we write this as 1 plus delta n for all n, right. If I add u of n to u of minus n minus 1, then this would be equal to 1 at all n. Is that clear? Very good. So, u of minus n minus 1 has a special significance. We shall come back to this later. And then finally, we have delay. Now, delay we shall represent by a special symbol Z inverse, which we shall discuss later, the significance of this, but it simply means that if you have an x of n as the input, this is x of n minus 1. In terms of hardware, it is a one sample delay. In terms of software, it means retrieving the immediate past sample. The immediate past sample is stored somewhere. If you require x of n minus 1, you retrieve it, you bring it back. This process is symbolically represented by a block whose transfer function is Z inverse. For example, if you have if you require x of n minus capital N, then you shall have to feed x of n to a chain of such delays. You do not write z to the minus n, there is no way we get z to the minus n. So, the symbol would be z inverse up to the last one would be the nth delay. Okay? This would be nth delay, this is the first delay. This is also a discipline that we shall follow. We will not write z to the minus n, we will write a chain of delays, n number of delays. A digital system, that concludes our discussion on digital signals. A digital system handles digital signals and operates on digital signals to produce another digital signal, which in some ways is better than what you had at the beginning. Let us take a very simple example of a digital system. Suppose you have an x of n which is scalar multiplied by B0 and added to a delayed version of x of n. If this is x of n, this is x of n minus 1. In such diagrams, you must indicate arrows, because arrows show the direction of flow of this signal. Okay? So, x of n minus 1, you multiply this by B1 and add it here. Okay? To make things a little more involved, let us say that we have another summer. We could have combined these two summers, but we do not do that. We use them separately, whose output is y of n. It requires another signal, and this signal is derived from y of n through another delay Z inverse and multiplied by, let us say, D1. Okay. Then you can see that y of n is equal to x of n B0 x of n, B0 x of n, then plus B1 x of n minus 1, then plus D1 y of n minus 1. So, this is the symbolic diagram for this digital system. In this digital system, the equation that describes it is a difference equation. You have x of n minus 1, you have y of n minus 1. This is called a difference equation, exactly like exact counterpart of differential equation in analog signal processing. Any dynamic system will be described by a difference equation, and a difference equation can always be represented by a schematic diagram like this. This diagram represents hardware as well as software. In terms of hardware, you require delay elements, you require multipliers, that is accumulators, you require summers, again accumulators, and in terms of software it shows what things are to be multiplied by what and which signal has to be retrieved from the storage. So, it is a hardware as well as software description of a digital system. We now look at the sampling process. We have already introduced small omega, the normalized digital frequency. We now look at the sampling process in a little more detail. I have already told you that if you have a, let us avoid that amplitude term capital A, if we have a cosine of omega 0 t plus phi, then from this by sampling and A to D, we do not show A to D because the mathematical techniques are the same for whether you have done quantization or you have not done quantization, and what you get here is cosine of n omega 0 plus phi, where omega 0 is 2 pi f 0 divided by f s. Okay. What happens? I have told you that f 0 must be less than or equal to f s by 2. What happens if this is not the case? We will illustrate with a simple problem. Let us say we have 3 signals, 6 pi t, cosine of 14 pi t. We can avoid phi also, make the signals as simple as possible. Let us say the other is cosine of 26 pi t. Then this is, what is the frequency, actual frequency? 3 hertz. This is 7 hertz and this is 13 hertz. When you sample, suppose the sampling interval is 0.1 second, all right, 0.1 second, which corresponds to Fs equal to 10 hertz. Obviously, 10 hertz is not the correct sampling frequency for the second and the third signals, but let us see what happens. When sampled, the signals become cosine of 6 pi t, this will become 6 pi n capital T, and capital T is 0.1, and therefore this will become 0.6 pi n, the first signal. The second signal will become cosine of 1.4 pi n, and the third signal will become cosine of 2.6 pi n. But 1.4 pi n is 2 pi n minus 0.6 pi n. What is cosine of 2 pi n minus 0.6 pi n? It is the same as cosine of 0.6 pi n. Similarly, 2.6 is 2 plus 0.6, and therefore this signal also becomes 0.6 pi n. In other words, the 3 signals become indistinguishable. This is what inadequate sampling frequency does. The 7 hertz signal now poses as if it is a 3 hertz signal. A high frequency poses as a low frequency. Similarly, 13 Hz signal poses as 3 Hz, and therefore, if the initial signal was a combination of 3, 7 and 13, the signal after digitization or after sampling becomes simply 3 Hz. Higher frequencies pose as low frequencies, and this process is known as aliasing, usually used in criminal language. So and so, a terrorist, alias so and so, alias so and so. Well, it is the same idea that has been taken here, that is higher frequencies, not a criminal. I mean, it could be as good a signal as the lower frequency one, but they pose as if they are lower frequencies, and the distortion due to this factor is known as aliasing distortion. Now, the way to contain aliasing distortion is to ensure that this quantity omega 0 is less than or equal to pi. If it exceeds pi, you see this exceeds pi, 1.4 pi. So, you could say 2 pi minus 0.6. If this is less than pi, then there is no problem. Okay. For example, suppose capital T is 0.02 second, that is Fs equal to 50 Hz. All right. Then what will be the signals? Signals would be cosine of how much? 0.12 pi n, cosine of 0.28 pi n, am I right? And cosine of 0.52 pi n. Agreed? And each of these, each omega 0 is less than pi, and these three signals are distinct. They retain their original frequency or the spectrum. What is the lowest sampling frequency which shall make the highest frequency omega 0 equal to pi? Obviously 1 by 26 Hertz. That is, capital T equal to 26 Hertz will make the last signal as cosine of pi n, right? And this essentially is sampling theorem. With the help of a very simple example, I have illustrated what the sampling theorem is. If the sampling frequency is not adequate, adequate means it's not at least twice the highest frequency content of the signal, then there shall occur aliasing distortion and the message would be distorted. There is no way that you can recover the original signal. Now we come back to digital systems. Digital systems. As I have already said, a digital system, a digital signal processor takes a digital signal x of n and does calculations on x of n and its previous samples to produce a new output y of n. Before we go into the formal characterization of digital systems, let us take a few examples. The first example that we take is an accumulator. Accumulator. An accumulator simply adds up the signals. It is the signal x of L, suppose it adds up from minus infinity, L equal to minus infinity up to the present instant n. This is an accumulator. One more signal comes, x of n plus 1 comes, it also adds it, two numbers. Okay? The previous number that has been accumulated to the present number. Okay? Now, I can write this in many different ways. One of the ways that I can write this is that if I change n, if I change n here to n minus 1, what shall I get here? Y of n minus 1. So, I can write this as y of n minus 1, and what am I missing? Plus xn. So, this accumulator can be described by a difference equation like this, yn equal to, where we have avoided the infinite summation. This is an infinite summation. Okay. We have expressed it in terms of finite quantities, a difference equation, but this equation is a recursive equation. Recursive. Why recursive? Because it requires recursion. Recursion is feedback. We have to compute the present output, we have to have the immediate past output, that is recursion, bringing it back from the storage. So, it is a feedback, and then add to the present sample. Whenever there is recursion, feedback, there is a possibility of oscillation or instability. On the other hand, this equation is non-recursive. This equation does not require past output to be brought back. Okay? This equation can also be written in a different form, y of n equal to summation L equal to minus infinity to n x of L. We can also write this as L equal to minus infinity to minus 1, let us say, x of L plus summation x of L, L equal to 0 to n. Agreed? Now, if you notice this quantity, what is this equal to? It is the output at n equal to minus 1. The upper limit n comes here. So, this is y minus 1 plus summation L equal to 0 to n x of L. Do not you see that this is the initial condition? That is, we start computation from L equal to 0, from n equal to 0, all right. This is y of n equal to this, but we have to take care of what existed before n equal to 0, that is the accumulator content at n equal to minus 1. Then we keep on adding. Depending on how we express this, you will see that the system characteristic is completely different. One is linear, the other is non-linear. You will see that a little later. Let us take another example. This is my favorite example, and it is upsampler. That is, if you want to change the rate of sampling, this is a very commonly used operation in digital signal processing, upsampling or downsampling. The samples were, let us say, at 10 hertz, if you want to change it to 20 hertz, or a 40 hertz signal to be downsampled to 3 hertz sampling rate. Upsampling and downsampling. Upsampling is determined by this equation, y of n. You see, once again we have x of n feeding to a digital system giving y of n. The relationship between y of n and x of n in an upsampler is y of n equal to x of n by L. For obviously this will exist when n is an integral multiple of L. Isn't that right? The digital signal exists only when the argument is an integer, positive or negative. So, this is for n equal to 0, plus minus L, plus minus 2L, and so on, and it is 0 otherwise. What does it do? What does an upsampler actually do? Let's look at a typical signal and see what an upsampler does. Suppose at 0 we have a 1, at minus 1 we have minus 1, and at plus 1 we have, let us say, 2. Plus 1. Okay. Suppose this is my signal x of n, and suppose L equal to 3, L equal to 3, L is an integer number. What happens to y of n? Let us try to draw this. At 0 it is 1, at 0 it is 1, okay, n equal to 0, 0 by 3 is 0. Then at n equal to 1, 1 by 3 does not exist. So, n equal to 1, it is 0, n equal to 2, it does not exist, n equal to 3, it exists and the value is 2. Yes, n equal to minus 1, it does not exist, minus 2, it does not exist, minus 3, it is minus 1, and the rest of the samples are 0. So, what has it done? It has not changed the picture. The picture is the same, it has expanded. How? It has padded 2 zeros in between every 2 samples. So, upsampling by a factor of 3 means filling up 3 minus 1, 2 zeros in between consecutive samples. We shall see later that this